Okay, so today we will talk about something we haven't done before. That is the induced. So this is so we have some projects which involve anapole susceptibilities of excited states and also some follow up for assessing the DFT functionals for based on their accuracy for computing anapole susceptibility. So there are two follow-ups that we want to do. So for the excited states, currently I've asked Pallav to start so that he gets familiar with the London package. So this is something over and above what Rahul is already doing. So Rahul is computing excitation energies or excited state energies as a function of field. And then we are looking at the intensities and then the orbitals involved in these excitations. So that's one aspect. Mommy. Now something else that we can do from the excited state energies is to compute the anapole moments or anapole susceptibilities of the excited states. So to go in that direction, and I will give some background today. Uh, so this is mainly based on uh, two of my papers. One is I don't remember the titles exactly. Okay, so one is the non-perturbative calculation of orbital and spin effects in molecules subject to non-uniform magnetic fields. This is a JCP paper, and there is a 2021 JCTC paper, which benchmarks DFT functionals for anapole susceptibility and also proposes a new criteria for classifying molecules and atoms as diamagnetic or paramagnetic, okay, which is more general than the usual one. Okay, that part I will not discuss today. I will only discuss the anapole moments today. So first I'll do some mathematical background and then I will tell you physically what it looks like. Okay, so let's start. So if I want to write a magnetic field, and let's say a non-uniform magnetic field, I'll use only a particular type of non-uniform field, that is where it is linearly changing. So it's not general in that sense, but so let's see. So what my field will look like as a function of the position vector
Ma'am,
r. Yeah.
you haven't shared your screen.
Oh, sorry. Wait. So I should share my screen. Yeah. Okay. So yeah. So the total field as a function of the position vector that has a uniform component which is same throughout space, and then I have a linearly changing part maybe to a matrix B, and then it is multiplied by, I'll write it explicitly as R minus some reference point H, and this is the matrix which contains the gradient. So what this basically is Z blah blah blah. Okay, so this is a matrix like this, and these are just some numbers. So it's just a matrix, and H is the reference point from which the gradients start showing their effect. So basically, when R is equal to H, then you only have a only the uniform part contributes to the field point, and when you go radially outwards from that, depending upon the matrix B, the fields change, and every component has changes in a different way. So you have 9 numbers which are in your hand basically to change this. This is a fairly flexible non-uniform field. Okay. And then there is a third term here that we need, which is 1/3 r minus h trace of b. Okay, this is because we want the divergence of b to be 0. Okay, because the field should it should be a, what is it called, a no work force should be generated from this field because it's a magnetic field. So that's why we write we have this extra term here. Okay, and the corresponding vector potential that you generate from this field, that is half of b total r cross r minus g. So what is g? G is now the gauge origin. So this is what we usually talk about. So this h is just a point that you select. Don't confuse it with the gauge origin. It is different. And g is the gauge origin that appears in the vector potential. Okay. And again from the, because there is a third term, this extra term, you get also 1/3 r minus h cross r minus h transpose b. Okay. So this is an extra term that appears, and you have to code it, but it's not problematic. It's fine. Okay. And we have the usual relations here also, that b is equal to curl of a. Now we'll talk a little bit more about the B matrix. So this B matrix okay, oh, let me say one more thing. So this H, if you shift around H, what happens is that the net field will change. I mean, the total field that the molecule is subject to will change. But a shift in H basically amounts to a shift in the uniform part of the magnetic field. So if you so H is arbitrary in the sense that it can be cancelled by a corresponding shift in B. So what I mean is that if I change H to H prime, then I can change B to B plus some other vector S, and I can choose S such that my B total R total prime is equal to B total R. That's arbitrary in that sense. But in a calculation, uh, since you basically input H, then like different values of H will give you a different field. So keep that in mind. But if you really need to shift H and keep the B total constant, you can calculate what S should be so that it gets cancelled. So that is about the field. Okay, now let's go to the first point. Then the second point is about the matrix B. So the matrix B has 9 elements. Okay, and it can be split into a symmetric part and a non-symmetric part. So any matrix basically so I can write this as half of B plus B transpose. That's half of B minus B transpose. So you can see algebraically that this is basically the same. Half B plus half B is B, and B transpose minus B transpose is 0. So that's fine mathematically. And then this part is called the symmetric part of the matrix, and this is called the anti-symmetric part of the matrix. So what is basically a symmetric and an anti-symmetric part? So if I have, let's say, 3 elements here, then if I have A, B, B, C, C, this is a symmetric matrix. And if I have X, Y, Z, A minus A, B minus B, C minus C, then this is an anti-symmetric matrix. So B can be split into 2 such parts. Okay. And then if I calculate and this antisymmetric part I can identify with the curl of the total field. So let me see. So I want to write the symmetric part as another quantity. So this epsilon is this what is called the Levi-Civita symbol in physics. In chemistry, we don't use it so much. What it basically is, it's like a 3-dimensional delta function. So if you have any 2 repeating units, repeating indices, for example, that is 0. If you have is equal to minus of epsilon, alpha, gamma, beta. So if you interchange 2 indices, you get a negative sign. And what else? And if you simply permute the indices in order, so gamma, alpha, beta, or epsilon, beta, gamma, alpha, those are all equal, and they're also equal to 1. So roughly, the relevant properties of the Levi-Civita symbol are these 3. And if I can define a vector C alpha as this. So this is basically a sum over repeated indices. So sum over beta gamma. Then C alpha is a vector, and this C alpha is an element of a vector, and the vector C can be identified as the curl of the total field. So what I'm saying is that B has 2 parts. One is the symmetric part, which scales the each component uniformly, and then there is the anti-symmetric part, which scales the field as if you are scaling it by a curl of the field. So and the curl part is basically the interesting part. Okay, so the linear shifts, those are fine. Those just those don't introduce any sort of what should I say, new physical property. They just change the strength at each point in a way. But the curl introduces some new properties, and it introduces like what like swirls in the electron density. that is the interesting part, and the anapole moments are related to the response of the molecule to the curl of the field. So that's why we do this separation, and then the reverse the reverse relation is where you have the matrix B. So an element of the matrix B has again a symmetric part, and it has a anti-symmetric part. This one. This is the reverse relation. And then what we do is we set the symmetric part to 0. So we set it to 0 because we are only interested in electronic properties related to the curl. Okay. So this was about the field, and now let's come actually to the anapole moment. So that is, so there are two alternative ways of expressing electronic moments or properties of any system in quantum mechanics. One is where you take an expectation value of an operator, and one is where you take a derivative of the energy. So this is in particular when we're talking about response property. So one is where you, so to compute electronic properties, we either do an expectation value of some operator, or we take a derivative of the energy as a function of some quantities. I don't know, let's see. I can put them as A, B, C. So these can be anything like electric fields, magnetic fields, whatever. And then you take a derivative with respect to one of them. Del, let's say, I yeah. First derivatives, or you can have second derivatives. Right? Dn, din. So this is a symmetric one. You can also have a mixed one. Okay. So these derivatives can give you the properties or the expectation value, and they are basically related by the Hellman-Feynman theorem. But for the Hellman-Feynman theorem to be exact, what you need is you need an exact wave function, which means you also need an infinite basis set or a complete basis set, and you also need a exact theory. So an exact wave function will involve an exact basis set as well as an exact model. So full CI, for example, if you took a full CI in an infinite basis, then the Hellman-Feynman theorem would hold exactly. But otherwise, these are not exactly equal. They are equal again for some particular theories, like Hartree-Fock. So for variational theories, again, you can show that this holds. But anyway, that is a separate discussion. Okay. But because we can do it in two ways, so we have both options in our hand. So now when we are subjecting a molecule to a non-uniform magnetic field, so what are the things that we have told it? We have said that there is a uniform component B, and there is a gradient with the 9 values in the matrix small b. And since we have set the symmetric part of this matrix to 0, then we can say that this field has just a curl C. So I showed you that the curl is related to the antisymmetric part of the B matrix. So only the antisymmetric part is there. The symmetric part is not there. So then I can say that for a molecule in a non-uniform field, my energy is a function of B and C. Okay. This is the uniform part. This is the curl. So these are the two inputs that I am given. And I can find from a Taylor series expansion in 2 variables, I can write EBC as a zero field energy plus half of the uniform component dot angular momentum with reference to the gauge origin. So let's say L minus G, or no, it's just with not L minus G, just with reference to L G. And I have a linear path. So this small a is the anapole moment which couples to the curl. So that is the definition of the anapole moment. So this is the anapole moment. And this is by definition the part which gets multiplied with the curl of the field. This is from where the definition arises. And then you have again the so-called second order terms. So now chi is basically the magnetic unity, the magnetic susceptibility. That gets you and if by 310 take account, then I write it as V transpose chi B. And because now we have second order terms. One is B.
Hello, ma'am.
Yeah. Yeah.
Your voice is breaking in between.
Oh, must be my internet. Let me just wait for a few seconds. Okay, is it better now? Sometimes it's unstable.
Yeah,
Is it better after that? Okay.
Yeah, it's good enough.
So this is the magnetic susceptibility. And now since we have C also, we have some other second order. So there's a next term which involves the coupling of the uniform part and the curl part. And the quantity in the middle, which is the property of the system, that is called the mixed anapole susceptibility. And there is another term which involves a quadratic interaction, only the curl, and then there is curl A, that is anapole susceptibility. And then, of course, after the second order, you have third order, fourth order, everything. But let's say stop here. So the quantities that I want to compute would be chi, m, and h. So these are the susceptibilities of the system. The angular momentum, of course, is there. So if you have a state with so p state with angular momentum +1, then the energy will increase in a uniform field. So that effect is given by this term. And if you only had a uniform field, then you would only have this term, then a third order term, etc. But if you have C, then you have these mixed susceptibility terms, and you also have a linear term which couples with the permanent anapole moment. I should clarify that. This is the permanent anapole moment. If the molecule has a permanent anapole. To have a permanent anapole moment actually is a very rare and special situation. So typically you would not encounter a molecule with a permanent anapole moment. So from here, let me draw a picture. Let me try to draw it at least. So what sort of thing is this anapole moment? So if you have a molecule which has a charge separation, then you get a electric dipole. So something like this. This is a electric dipole. Okay. Similarly, if you have a magnet with north and south pole, this is a magnetic dipole. If you have a charge that is moving in a ring, some charge, plus or minus or whatever, then it generates a magnetic field, right, along the axis. So this is also a magnetic dipole. Okay. Now, if you have a toroid, this is now a little bit difficult to draw. Okay. If you have a toroid and you have let me just open the picture and draw it properly, because one minute. Yeah. So there is a when you have a toroid, the current you can have that is going along the axis. So you call that the axial current. So the charge can be moving there, and you also have some charges which are moving along these small rings. These are called meridional currents. So this is what is called axial current. And this is what is called a meridian current. Okay. And then what you generate from the axial current, that is same as this magnetic dipole. So that's the ring current, and you generate a magnetic moment here. You generate a field corresponding to the moment, and then or I don't know what to call it, maybe small m. Okay. Magnetic dipole. So the direction in which the current generates a field, the moment is in the same direction, and the contribution to the energy is a dot product of the two, right? But these meridional currents, in case of a toroid, they can also create a field or a moment, no, I can't say it's a field, it's the moment that is along the axis of the, not, yeah, along the, what is it called? The perpendicular axis of the ring. And this is the toroidal moment. Okay. So this is the sort of classical analogy of the anapole moment. And this toroidal moment is also called the anapole moment. So people did not realize this, the existence of this moment. So people did not realize the existence of this anapole moment for a long time, and till about 1954. So before that, all the expansions for energy in terms of moment, those did not include the anapole moment. So they were not wrong, but they missed this anapole term. In 1954, this anapole moment was sort of discovered, and after that it had existed, and it's not studied so much. Okay, because non-uniform fields themselves are not studied so much because it's so difficult to control it. So experimentally also, if you want a particular type of non-uniform field, it is very difficult to do. So not many people study it experimentally. It suddenly became very interesting when the CP violations started to be investigated. So, but those are the nuclear anapole moments. Okay, the nuclear anapole moments, they have a they are the source of CP violation in a way. So people started studying nuclear anapole moments quite a lot, and that the research has been growing over time. But what we are doing, of course, is not nuclear anapole moments. We are doing electronic anapole moments. So this is even less studied. So only the few groups are doing this. One is, of course, the Oslo group, where I did my postdoc. Then there is a group in Italy, and there is a group in Spain. As far as I know, there are these three groups who do theoretical research on anapole moments. And on the experimental front, there is something called metamaterials, which are now being designed. So uh, I am not very sure of exactly what they are, but they're basically very tiny systems subject to very tiny fields, but they are analogs for real materials. And because they're so tiny, you can sort of get a particular and measure the toroidal moment, etc. So this metamaterials is a very sort of frontier field, and they have different applications. Uh, I mean, metamaterials themselves have a very wide application in engineering and physics and whatever. But metamaterials have also been used to generate and study toroidal moments. So our interest in metamaterials would be from that angle whenever they study the toroidal moment. Okay. So recently some experimental possibilities are cropping up, but still it's quite far. I mean, electronic anapole moments are still an entirely theoretical domain. Okay. And then anyway, so so physically, basically, they are toroidal moments, the anapole moments. Now, in the case of molecules, having a permanent anapole moment is pretty difficult, like I was saying. So either you need a charge distribution which looks like a toroid, so something like a toroidal molecule, and that would have a permanent toroidal moment. Or what has been found out from, I believe, group theoretic arguments is that if you have a chiral radical, you can have a permanent anapole moment. Okay. So that is, those are the two classes of molecules that can have permanent anapole moments. But both those classes are very difficult to handle theoretically with the machinery we have now. So what you need is basically a you need a code which can handle non-uniform magnetic fields completely, including spin as well as uh, two-component orbitals, complex algebra, all the. But it must be also be computationally efficient. Toroidal molecule. So just to make a toroidal molecule, you'll need a very large number of atoms. So that's going to be computationally very expensive. So that's one thing. Also, the accuracy would be hampered. If you have many electrons, you need more, like you would need a correlation theory which includes uh, the correlation effects, and you need to have basis sets good enough, blah blah blah. So it's theoretically still very difficult to study permanent anapole moments. What can be studied and what we have studied is induced anapole moments arising from the susceptibilities. So what we compute is basically M and A. And these susceptibilities of the molecule tell you that you can have an induced anapole moment when you subject the molecule to a non-uniform. So this is where we are at the moment computing this. So as you can see, since the energy is related directly to these quantities, one way of computing these would be to take derivatives of second derivatives of the energy. So if you can get energies for various values of B and C, by taking suitable derivatives, you can compute M and A. So that is the path we will follow for the excited state anapole susceptibilities after we compute the excited. So that basically means we will compute these quantities. So the susceptibilities can be written as, so let me just first write the usual one. The ordinary magnetic susceptibility with respect to just the uniform field, that is the second derivative of the energy with respect to the components of the uniform field. Okay. Evaluated at B equal to 0, C equal to 0. Okay. Similarly, you can have A alpha beta. Or basically C equal to 0. And you can have the mixed one. Now, because of the definitions that we've taken, both in the energy expansion as well as in the operators, I like the operators in just a minute, we have some additional signs and factors. So the susceptibility has, magnetic susceptibility has a negative sign. Then the anapole susceptibility has a -2 factor, and this one also has a negative sign. Okay. And since they are second derivatives, you can also express them as first derivatives of the induced anapole moments, for example. So then you can write this A as a del del C of A alpha. This is, I'll write this with a prime. So this is induced Anapole moment. Sorry. Now, why am I writing this expression? So you can compute and what are called analytic derivatives of a theory and evaluate the induced Anapole moment as an expectation value directly. So this is sort of a mixed approach where the induced Anapole moment is computed as an expectation value of a wave function, and then the second derivative is taken numerically. In this case, you just, in the first case, here, we compute E as an expectation value for a given theory, which will mostly have the Hartree-Fock or DFT in our case. And then you take a numerical second derivative. So this is one approach. The second approach is where you compute the Anapole moment as an expectation value. So you take a and then you take a first derivative with respect to the other. So why we do it? So why we do this is because we don't have analytic second derivatives available in London. Okay. So if in principle you could also have evaluated the susceptibility directly as an expectation value. If you had the analytic, so-called analytic derivatives available. So that means implementation of the expectation value operator corresponding to this quantity. Okay. So this is one. So I can maybe call this something different. And then M alpha beta prime. This has a minus half in the definition. And this can be a first derivative of the angular momentum. So momentum is a first derivative with respect to B. So the numerical part will be with respect to C. And since this is a mixed one, you can also go the other way, which means that I take the analytic Anapole moment, induced Anapole moment, which is then this, and I do a, so this is, okay, if I want to keep the same alpha beta as before, so this is beta, and this will be alpha. So this is now again, so for the mixed susceptibility, you again have two options. So there are three kinds of three numerical values for M and two for A that are possible to be computed for the ground state. Okay? Because the analytic derivatives are available in London for the first derivatives for the ground state. For the excited states, we only have energy. So the only option is to use these three. So far we have been talking directly about the derivative form. Now what we need to know is the operator forms of the quantities I've been talking about. So how do you obtain the operator forms of this? So basically you take a derivative of the Hamiltonian with respect to B, with respect to C, etc. And when you do that, and then you manipulate things a little bit, you get the operator forms of the these quantities of the moments. So what you're familiar with is the angular momentum, for example, and operator is basically Rg, or I did not introduce this notation, so R minus G cross I. Pi is the P minus E. Okay. This is called the physical momentum. G is the gauge origin. So this is the angular momentum operator. And is there something else I should mention? Okay, so this is the total operator. Of course, I have to sum over all the electrons in the system. Yeah. Okay. Also, although we do take the angular momentum with reference to the gauge origin, because that is already available to us, the definition of the operator can be with respect to something arbitrary. That does not matter. So Q is just an arbitrary point with respect to which you define the angular momentum. Okay, so this is the first quantity. Next one is the A operator. So if you want to compute this A prime alpha, you have to take an expectation value of the A operator. So what is the A operator? The A operator is, again, we have to sum over the electrons now. This is the operators. R minus H cross 1/3 of LH for electron L. Okay. So this is the Anapole moment operator. So how we are getting this is by taking a derivative of the Hamiltonian with respect to C. After we put in the expression of B total in the Hamiltonian. Okay. That's about it. And so the quantity A then is psi A psi. But this is something we cannot do for the excited state, I repeat. So that's basically the background of Anapole moments. So I introduced a lot of new things, I think. So do you all have any questions now? Or something that you didn't understand? Yeah.
The total expression, that is the first B total vector. First expression, how it is come from the first B vector plus R vector minus.
Oh, it has not come from somewhere. This is the magnetic field, the non-uniform magnetic field form that we are taking. This is a general expression for a linearly changing magnetic field. It is not coming from somewhere. So the field that we are applying to the molecule has a uniform part, this one, and it has a linearly changing part where the changes are put into the matrix field. And then that is scaled, of course, by every point, or the distance of every point from H, where H is the point where you only have B. This is it's a general thing. It's like writing A to A plus dA dx into x. It's a linearly changing magnetic field. Do you get this?
So first term is for uniform field, and second term is how the
For the
field.
changing.
Okay.
Yeah. So the first one is just a vector. It's some b0x, b0y, b0z. Whatever strength you want.
First case, there's maybe another term because of the this is the first order derivative term in the B expression. There is a for matrix form. So for all coordinate changes del v x by del x. So there may be some term that is for second order, just like the Hessian matrix type, and a second order.
No, this is a linearly changing field, so we have not taken second order variations.
Okay, okay,
So this is particular, like I said, this is not a fully general non-uniform field. We've only written up to the linear change.
okay,
If
okay.
you want, you can write second like Hessian change, triple, whatever. But that is too complicated to handle at the moment. I mean, if you're interested, you could do it. It's not outside. It's not impossible. You could add a term and then evaluate all. But they will again be different properties. I mean, if you are only interested in anapole moments, it's sufficient to use up to linearly changing. Because what you need is just the curl of the field. If you want to say, what is it called? Uh, Curvature, like some response property with respect to curvature of the field, then you would need a second order changing field, like a Hessian. And not a Hessian, but yeah, like second order gradient. And what is it called? Yeah, curvature. Yeah, that is the word. The curvature of the field. So here the field does not have a curvature. It only has a gradient. You get it?
And in the last picture that you showed,
Last,
in the
you want
last,
me to scroll?
uh, oh, school high, yes, that is that picture. In the last, there is a, you said there is a axial current is there around the toroid. Uh, so there is due to the motion around the orbit in the loops, just like loop. So there is magnetic field is generated for but along the toroid. So there is also a perpendicular loop. So that uh, uh,
Can I call
uh,
it? Yeah, I can call it a perpendicular loop.
loop. So for this perpendicular loop, so there is another magnetic field that is you say the anapole susceptibility, right? No?
The anapole moment, yeah, of the
Okay.
toroidal moment. So classically, it is called typically toroidal moment nowadays.
Okay.
The original term was anapole moment, and that term has survived in quantum studies. But now, in the classical domain, it is called a toroidal moment.
Okay.
Yeah, but they're basically the same thing.
Oh, so there is a two arrow, and the first one for uh, anapole moment, another for orbital. That's not right. You
Another
define.
for the usual magnetic dipole moment.
Okay.
So in a toroid, you have like two kinds of moments generated,
Okay. So this.
and they interact with the field in a different way. So the M, which is the dipole moment, that interacts with the uniform part of the field, which is along the same axis. But this T, it interacts with the curl of the field if it is there.
Okay.
If you subject the toroid only to a uniform magnetic field, then the toroidal moment will not interact. It will not show up. Only if your field has a curl, then this toroidal moment will interact.
Okay. And this anapole moment is showed for some special type of molecules, no? Right?
Yeah. So if you
For
want a permanent toroidal moment that interacts directly with the curl of the field, then only special types of molecules can show it, and it has not been experimentally demonstrated. So this is only a proposition
okay,
that it is there, theoretical proposition.
okay,
But theoretically, quite a few people have done it. Like there is what is it called? I'm forgetting the names of the molecule. There's cyclo. Uh, no, wait. There are some like chains of molecules. This I forget what they're called. Let me see. I'll tell you the names of the molecules which have been demonstrated to have permanent magnetic moment. 1 minute. It's called this single molecule magnets. There is something called dy, dysprosium or something. The clusters of those have been shown to have toroidal moment, and some actually like a toroidal shaped molecule that has also been shown to have toroidal moment. But actually subjecting them to a field and seeing how they interact, that has not been done.
okay. So that means the electron will move not along the axis. So that may be moves with loop formation. So,
Yeah, it will move in this sort of loop along the thickness of the toroid.
okay, okay,
I mean, if this is a molecule, then the electrons are anyhow moving in all kinds of directions. But the different motions, they generate moments in different directions.
okay,
So the part of the electron motion that is axial generates the magnetic dipole moment. The part of the motion that is, going in rings along the thickness, that generates the toroidal moment.
okay, okay. It's okay.
Yeah, uh, it's okay. Okay. Any more questions? No. Okay. So next time, when we follow this up, we'll talk about more about practical matters, about how we'll go about this. This is basically the background of what we want to do. You can look at the videos also if you want some more details or to complement this, and also the calculations if you like. And of course, again, I have not done every step. Okay, I wanted to finish in 1 hour, so I haven't done the steps between. If you think something is not straightforward, like some step, let me know. Like you, for example, the fact that this the third term is responsible for the third term in the magnetic field expression, that is responsible for making it divergence free. You can straight apply the divergence onto the field and check that it is the case. Back calculation is quite difficult, so better to just verify that this is correct. Other things which I have left out is this operators, like how derivative of the Hamiltonian gives you the operator. This also you can try on your own. If not, let me know if you're not able to do it. Or this is again just to understand. For doing the work, you will not need to do this derivation. The project itself is largely application and numerical, but the background is a little bit different from what you normally study. Good to understand it in detail. And Nikhil, when you have time, you can also, or after follow-up progresses somewhat, then you can join so that we run things quickly. And Rahul can help maybe follow-up to run the code in the first place, because that is what he will need to do. I mean, the outputs will be the same for Rahul and follow-up, only he will work with the data a little bit differently. Okay.
Thank you, ma'am.
Okay, so I'll stop the broadcast then, and I'll stop the recording as well.